So let's take a look at taking some of these concepts that we have about lines and planes in space and applying some calculus properties to them. Now, some of this is stuff that you're just taking things you already know and applying it to a new situation. So I just want to make a quick mention about these vector-valued functions. Vector-valued functions just plot trajectories that you're going through space, but each of those coordinates depend on a third variable. So that variable usually is t. And so it turns out that wherever you are as you're moving through space, your location x, y, z depends on time, or whatever that variable happens to be. If you're going around a unit circle, that t could be the angle measure. That means that each of those components, the x, y, and z, are all dependent variables, and the independent variable is not the x, not the y, not the z, it's actually the t. So when you have it written like this down the bottom, where r of t equals x of t, y of t, z of t, then those x's, y's, and z's are actually dependent variables, even though usually we don't think of x as the dependent variable. You can look through, I got some information there about how to graph these things, some facts about derivatives. I'm pulling this up here for one specific purpose, which is if you take those derivatives of that vector-valued function, you take the derivative by deriving each of those components individually. So you do x prime, you do y prime, you do z prime. What you're coming up with is the tangent vector. And if all three of those functions are differentiable and the first derivative is not zero, then we say that r of t is smooth on that interval. All right, so I'll let you go through and examine each of those individual pieces. Suppose I've got this function r of t. It's got an x component, a y component, and a z component for t values that are greater than 0, which I just put in here to make sure that we're not trying to take natural logs of negative numbers. Find r prime of t. Well, r prime of t is going to be the derivative of the first component, so 4e to the t, going in the I direction. There's not going to be a derivative here, right? The derivative of a constant is just 0. What's the derivative of the natural log in terms of t? 1 over t, and that will be in the k direction. Okay. This guy down the bottom says if r of t equals t squared, t to the third, t to the fourth, find r prime and r prime of 0. Is it smooth? So r prime of t seems like an easy thing to do, right? Power rule, 2t, 3t squared, 4t to the third. Looks even easier to find r prime of 0, which is just 0, 0, 0. So the first derivative is equal to 0 at t equals 0. Is it smooth? No, because the rule was that the first derivative at 0 could not equal 0. So what that means is that if 0 is a critical point, it may change direction over there, but I have no guarantee that it's actually changing direction. All I know is that the derivative at 0 is the 0 vector. All right, the unit tangent vector is going to show up a lot, not only now, but in the rest of this chapter and as we move on. What is the unit tangent vector? Break it down. It's a tangent vector, so it goes in the same direction as the vector, just like a tangent line touches a line at a certain point. The tangent vector touches the vector at a point, except that it's directional. So it has to go, if the curve is going this way, the tangent vector at a point has to go in the same direction as the curve. All right, so assuming that that curve is smooth, it can be written in terms of t, so it's parametrized. Then that unit tangent vector is the derivative over the magnitude. So it's a vector that goes in the same direction as the curve that is 1 unit long. Now, the unit tangent vector has no units. Numerator and denominator have the same unit, so they cancel. So if your r prime was measured in feet, then your magnitude would also be measured in feet. Feet and feet cancel. Unit tangent vector, oddly enough, has no units. All right, so let's take a look at this first one. The first one says the unit tangent vector for cosine t, sine t, and 2. So the first thing I need is I need the derivative. So r prime is going to be the derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of 2 is 0. Okay. Now, if I want a unit tangent vector, so that's r prime of t, I need to find the magnitude of r prime. Well, look what happens here. I get the square root of a squared plus b squared plus c squared. So the square root of negative sine t squared plus cosine t squared plus 0. Isn't sine squared plus cosine squared equal to 1? Oh, so this is its own unit tangent vector because it's already a unit long. First example was a trick question already. Look at that. All right, the second one now wants a unit tangent vector for something that looks similar but is a little bit different and wants it at a specific point at t equals 0. So the first thing is, let's find r prime of t. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of e to the negative t is negative e to the negative t. Remember the chain rule, you multiply by the derivative of the exponent, so it becomes negative e to the negative t. All right, let's turn this into some numbers. So let's find r prime of 0. Cosine of 0 is 1. Sine of 0 is 0. What happens to this third guy over here? When I do negative e to the 0 power, e to the 0 power is 1, so this gives me negative 1. So my r prime of 0 is 1, 0, negative 1. What's the magnitude of r prime of 0? Well, it's going to be the square root of 1 squared plus 0 squared plus negative 1 squared. So it's going to be the square root of 2. So the unit tangent vector evaluated at 0, remember, is going to be r prime of 0 divided by the magnitude of r prime of 0. So it's going to be 1, 0, negative 1, each entry divided by the square root of 2. So the unit tangent vector is going to look like this. 1 over root 2, 0, negative 1 over root 2. You can actually pull the 1 over root 2 on the outside and just leave those things on the inside, but that guy down the bottom right corner is the unit tangent vector. It's 1 unit long, and it's tangent to the curve. All right, this I put up here because this is a special formula. You'll see this in one of the slides as you go through. How do you take the derivative of a cross product? The derivative of a cross product is down here. So the derivative of u cross v, it looks a lot like the product rule. So it's u prime cross v plus u cross v prime. So it's the product rule, except that instead of multiplying, you're doing cross products. So my first thought was, let's write this as two vectors, because I don't like the i's and the j's sometimes. They kind of get in the way. So vector u is going to be t cubed negative 2t negative 2. All right, so I got my I, I've got my j, I've got my k. My vector v is going to be t negative t squared negative t cubed. All right, so what's my rule? My rule is to take u prime cross v. So u prime, so let's make my I, j, and k. U prime is going to be 3t squared negative 2, 0, and then v is going to be t negative t squared negative t cubed. Now I got to find the cross product of that guy over there. So I end up with 3t squared, and now look at the 4 pieces that are left. Really, I only need to multiply negative 2 times negative t cubed, because that'll give me a positive 2t cubed. That's in the I direction. Now minus j times what? 3t to the 5th with a negative, so negative 3t to the 5th. And then k, that one actually has 2 parts. So negative 3t to the 4th, and then minus a negative 2t, so plus 2t. All right, so the first part comes out to be, if I write it in vector form, 6t to the 5th, 3t to the 5th, and then the third component is just going to be negative 3t to the 4th plus 2t. All right. then you can take it from here. The next one would be another cross product representing this second piece. Right? So I did the cross product for the first piece. You do the cross product for the second piece, and then add those components together. So it's going to be a little bit of a messy answer, but that's how you do it. So set it up for the first one, then set it up for the second one, and then add them together. All right, if we can do derivative rules, we can do integral rules. Integrals work just like derivatives, except in reverse. The only fun thing is that sometimes you may have initial values. So let's take a look at this second one over here. If I give you r prime of t, and here's your first component, there's your second component, there's your third component, how do you evaluate that? Well, the first thing is, each time you do one of these, you're going to pop out a constant of integration. So r of t is going to be what? If this is t to the 1/2, and you take the antiderivative, you add 1, divide by the new power. Well, instead of dividing by 3/2, I'm going to multiply by 2/3. So my first component will be 2/3 t to the 3/2 plus a constant. All right. How do I take the antiderivative of cosine pi t? So I'll end up with the sine of pi t, but remember that there's a chain rule involved here. So sine of pi t divided by pi plus a different constant. Maybe, maybe not. All right, the third one, when I take the antiderivative of 4 over t, I get 4 natural log of t plus a third constant. And now for each of them, I need to evaluate it at 1, because here it tells me this is my initial condition, that r of 1 equals 2, 3, 4. So if I put a 1 in here, I get 2 equals 2/3 times 1 plus a constant. All right, so 2 is the same thing as 6/3. So 4/3 is my c sub 1. Over here, if I put in a 1, I get the sine of pi over pi plus a constant equals 3. Well, what is the sine of pi? Oh, all right. Well, that's not terrible, right? The sine of pi just gives me 0. So 0 plus 3 is 3. My second constant is 3. Over here, I get 4 times the natural log of 1 plus a constant equals 4. Well, the natural log of 1 is 0. C sub 3 is equal to 4. All right, so what's my answer? I'm going to put my answer up at the top here. R of t equals 2/3 t to the 3/2 power plus 4/3, right? That's my first component. My second component is going to be the sine of pi t over pi plus 3. And then my third component is going to be 4 natural log of t plus 4. And I really should put the t in absolute value brackets. All right, so that's what I get. So when you take the antiderivative, you're going to pop out constants of integration for each part and then evaluate it at the given t value. Put those numbers in on the other side. All right, let's see how we're doing here. This is just a reminder about how to find velocity and acceleration. If you have the function, derive it once to find the velocity. If you want the speed, that's the magnitude of the velocity. Right? So take the velocity vector, right? The velocity vector will be a component vector, right? So take the derivative here, and I'll end up with a 5t. This will give me a 12t, and that's my velocity vector. The magnitude of the velocity then will be the square root of a squared plus b squared. The acceleration will be a vector. So you have vector, scalar, vector. All right, circular motion. In 2 dimensions, you're moving around a circle. 3 dimensions, you're moving around a sphere. So if you're in 2 dimensions as you move around the circle, then you can take the velocity and you can take the acceleration. And when you start taking dot products, interesting things happen. So if the velocity, if the position is cosine sine, the derivative of cosine is negative sine. So you get negative a sine t, a cosine t. And then the acceleration is going to give you negative a cosine t, negative a sine t. Right? If you take the dot product of r and v, you're going to end up with what? I'll do one of these, right? If I take the dot product of this, I'm going to end up with negative a squared cosine sine plus positive a squared sine t cosine t. And what happens? I have exactly the same entry with two different signs between them. The dot product is 0. So it turns out that the dot product of the function and its velocity, and also the acceleration and its velocity, are 0, which means that those tangent vectors are perpendicular to each other, right? If the dot product is 0, the two vectors are orthogonal. All right, initial value problems, we kind of already did this, right? If you know the acceleration, you can work backwards to get the velocity. If you know the velocity, you can work backwards to get the position. But this is an R2. It looks like a relatively easy thing, so let's take a quick look at it. If I know the acceleration is that constant vector over there, then the velocity at any time t is going to be t plus some constant, 2t plus some constant. Now it tells me when t is 0, the velocity is 1, 1. All right, so now I can see that if I fill in a 0 for t, I end up with c sub 1 is 1, c sub 2 is 1. Easy because these are polynomials, don't fall into the trap. I could give you e to the x's and sine x's and cosines, and that's not always the case then. All right, so now this becomes just t plus 1. This becomes 2t plus 1. Velocity, right? You want position, find the antiderivative of that. So the position vector at time t is going to be t squared over 2 plus t plus a constant. Technically, I should call that 3. And then this will give me 2t squared over 2, so t squared plus t plus a constant. If you put a 0 in for t, right, now we're using this initial condition here, it turns out that that's c sub 3 and that's c sub 4. So my position vector, my vector valued function, is just t squared over 2 plus t plus 2. That's the first component. T squared plus t plus 3. That's the second component. So work backwards each time. Each time you do that, you will end up with a constant of integration for each part. All right, three-dimensional motion. Let's take a look at this, and I think I'm going to try to solve this on a regular whiteboard. So I got a baseball hit 3 feet above home plate with an initial velocity of 30, 30, 80. The spin on the baseball produces a horizontal acceleration of 5 feet per second squared in the northward direction. Find r of t. So the first thing is I need to find a of t. When I find a of t, I've got to remember that there's such a thing as gravity. And so, sure, the acceleration at time t, nothing in the first dimension. It's got an acceleration of 5 feet per second that's horizontal, so that's in the second dimension. And then gravity is pulling down at an acceleration of negative 32. So I've got that. The other information I know is that the velocity vector at time 0 is 30, 30, 80. Right? If that's an initial velocity, then I've got that. And the other thing I know is that it's hit from 3 feet above home plate. So initially, r of 0, 0, 0, 3. Okay. Let's use that information to find the vector valued function. All right, I'm going to switch over to a blank board over here so that I can have some space to write. All right, so my acceleration vector looks like this. The acceleration at time t is 0, 5, negative 32, which means that the velocity at time t is going to be, well, the antiderivative of 0 is just a constant. That's going to give me 5t plus a constant, and that'll give me negative 32t plus a constant. Now, we know from the problem that the velocity at time 0 is 30, 30, 80. Okay. Nothing funny happens in this problem. If I put a 0 in for t, c sub 1 is just 30. C sub 2 is 0 plus 30, which is 30. And that's 0 plus 80, which is 80. So it turns out the velocity vector is pretty easy to find. It's 30, 5t plus 30, negative 32t plus 80. All right, from there, let's see if I can find the position. So for this, I'm going to have to find an antiderivative again. So the antiderivative of 30 is 30t plus some constant. What do I use? 3, so let's call this c sub 4. This guy over here will give me 5t squared over 2 plus, don't forget, 30t plus a constant. And the last one will give me negative 32t squared over 2. So t squared over 2, let's make that negative 16t squared plus 80t plus a constant. Now, remember before I switched slides, we had said that the initial position over here was 0, 0, 3. So it's hit 3 feet above home plate. The first two are just going to produce constants of integration of 0, right? That'll give me a 0. If I put in zeros here, that gives me a 0. But this doesn't. This actually pops out a 3 in that third spot. So I end up with the vector valued function being 30t, 5t squared over 2 plus 30t. And then this last one comes out to be negative 16t squared plus 80t plus 3. Maybe this is starting to look familiar if you took a physics class. That third dimension over there is starting to look like negative 1/2 gt squared plus initial velocity times time plus initial height. All right. So let's look at two other things that I can come up with. And that is I can come up with time of flight and range. All right. I need the time of flight in order to get the range. Time of flight is how long the ball is in the air. So in other words, figure out what happens when z is equal to 0. So I get negative 16t squared plus 80t plus 3 is equal to 0. Quadratic formula is going to solve this. I'm going to spare you the sitting and watching me do the calculations because I already calculated this in advance. It turns out t is equal to 5.04 seconds. So that's how far it is up in the air. Some of these you can do completing the square or something like that, but this one seems like the quadratic formula is going to be needed. So that's how long it goes in the air. Now, what if you want the range? The range is just the magnitude of the vector valued function evaluated at 5.04. So the first thing is you need to find out what r of 5.04 is. Take 5.04, put it in here for t. All right. Again, just to spare you some of the details, I calculated already. I got 151.2. I got 214.7. And not surprisingly, I got 0 for the third component because we got the 5.04 by setting z equal to 0. And then the last thing is just to find the magnitude of r, evaluated at 5.04. So take the square root of 151.2 squared and 214.7 squared, and you end up with about 263 feet. All right, so that's the range of this baseball that's thrown up in the air, and that all happens within 5.04 seconds. So in other words, it took that baseball a lot less time to hit the ground than it did for us to figure out that information. But that's how you do it. It's just a process of working backwards. Organize your work, keep track of those constants of integration, and then once you get the formula, then figure out what we need it for. All right, and if I'm thinking, that should be the last one on there. Yep. All right, thanks for watching.